Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 15. Students, in this lecture, basically, I'm solving an assignment. Okay, this is also basically a demanded assignment. Okay, so basically, where that assignment is, let me show you where is that assignment. Okay, here we have. So this is basically an assignment. Okay, and I try to solve it. Okay, so you see that we have basically this assignment is, you can say, relevant and related to our question number 1, lecture number 1 and lecture number 14. Basically, figure shows, okay, 10 feet and your dead load, live load, okay, shows a simply supported beam spanning 30 feet with a concentrated loads at the third points. This is important. Third points means you have to divide your span length into 3 equal parts. The span. Each load consists of a dead load component of WT, this much, which includes an allowance for the weight of the beam. This means that you have to include basically the self weight. The self weight excluded mean that the self weight is not included in this weight. When a live load is this much, the beam is continuously braced on its compression flange and as a yield stress. This is, you can say, a good news for you people. Continuously braced means LB equals to 0. Okay, this is one good news. Okay, your LB is now equals to 0. Clear? This is one determination. Find the lightest W18 section that will limit the deflection. This is, you can say, a bad news because you have to check serviceability limit. Using strength level LRFD load combination, find the lightest W18. Here you are bound that you have to find the lightest W18 section. Okay, so this is a design part, clear, and you can say here you have to check basically section, clear. Adequate pleasure capacity. So let's start. I have basically I have write down the data. You see here span, dead load, live load, yield strength, and beam is continuously braced. Okay, lightest W18 section, but delta should be less than in this one, and flexure capacity. And you see the section, okay, the beam, okay, and the stiff, as usual, you have to find out PU, and 1.2 you have to add up this one, okay, and you have to add up means that your dead loads plus this split plus this dead, okay, you see here, and your live load you see here, okay, and you have to factor it. So remember, this is not UDL, these are concentrated load. Okay, so one thing I explain here, please, those who are watching first time this lecture, please revisit my other lectures, that is lecture number 15, lecture number 14, 13, 12 and 11, and lecture number 1, 2, 3, 4, 5. Those all lectures are relevant to this question. So therefore I'm not explaining things, I'm just go through it. Okay, so because I explain all these things in those lectures, clear. So now moving forward, and let me show you other things. We have PU is 60 kip, okay, and now PU, okay, you have to find out, because you have to check deflection, so you need to find out your live load, okay, and then they determine the reactions, okay, they are simple because you know that the beam is simply supported, clear, and half loading will be this side and half loading will be this side. Means if you have total 60, so 30 will be this side and 30 will be that side. So basically you don't need to be confused. You have to find out your MU, and MU is nothing, you already know that these are the point loads, and the diagrams will be looks like, I think so, this in this fashion. This will be a moment diagram. The maximum moment will be right at the support, right at the concentrated load. In between these 2 points, the loading will be uniform. Clear? And what you have to do, you have to find out, okay, reaction, you got it. So you just need to find out the moment, and that moment will be 30 times 10. Clear? So this is easy. Now you find out your reaction, that is your movement, that is 3600 kip/inch. Clear? Now next, we got the moment, and now we have to determine the maximum deflection. Okay, so remember from AISC manual chapter 4, basically you can see this formula, you can search this formula. Clear? In previous lecture I show all these formulas, and you just need to search it. At the end of the lecture I try my best to show you these formulas. Okay, so we have 2 point loading. So for that purpose, as you see in my previous lecture 14, 12, we have UDL loading. So for that we are using different deflection formula. For point load, which is affecting at the mid, different, but here we have 2 equal at third points concentrated load. So for that purpose we have to determine, we have to use this formula. Now in this formula, basically if I draw the section, for example if I have simply supported beam and there are third point movements loads, okay, so I think so this is A. Okay, this distance is A and L is the total distance. So that's why they basically use, you will see here, mu is equal to phi mn is equal to phi mp, and here you have the maximum movement. Important note, as the beam is continuously braced, therefore LB will be this, and that suggests that basically your LB will be lesser than LP. So it is also a good news that your movement capacity will be MN or MP will be Fy times Zx. Clear? So you don't need to use those lengthy formulas. Okay, so this is good news. Now you see we have a simple formula, and here we are going to select the section on the basis of Zx criteria. Okay, on the basis of plastic section modulus. Clear? Now we find out the Zx as we did in question number 1, lecture number 1 basically, and now we have to choose such a section which have a Zx, basically you can say larger than or equals to 80, but select such a section a little bit greater Zx. Okay, now Zx is 80 cubic inch, so you need to go to the table and find such a section having a section Zx greater than 80 or equals to 80. So let me show you that where is that Zx. Clear? So this is still manual. Okay, and here we have basically Zx table, and we required basically 80. Now remember this is 0.9. Clear? And 36, I think so we have 36 steel. Clear? So we have to choose what section, let me check it, W1850. Clear? So from there we will confirm. Okay, we will confirm them that how W18 section, this one, 18 lightest section, remember. There are decreasing now 1840, okay, and 1846 basically having a modulus section, modulus ZX plastic section modulus 101. This is the lightest section, remember. This bold black color basically representing the most lightest section, clear? And the next one is 1850, and the next one is 1846. 1846, where it is, 1846 is a larger one, okay. 1846, this one, but remember this is not a lightest section, remember, and it has 90.7, clear? So this is the way how we got these values, clear? Now let us select W1846. Although this is not a lightest section, but in part 1 basically we are not bound to select the lightest section, clear? We are allowed to use whatever the section, clear? We have to check the compactness of the section, okay. Let us see, we check it. Lambda, you know, BF divided by 2TF, that is 5. From where it is come, you just need to go to the table of your manual, okay, at the first chapter, in the first chapter, and you search the section that is W1846. W1846. Scroll down, scrolling up. Here we have this one, and the first term, here we have the first one, I think so. No, not the first one. Where this one, the last third one, this one. So here you see this is BF divided by 2TF and H by TW. We required both these two values, clear? And here you see 5.01 and 44.6, clear? So this is the way how we select it, clear? Coming back, you see 5. Lambda p is 65 divided by f1 into root. From where we got these equations? Okay, you must watch my lecture number 1. I explained these things. Okay, you got 9.19. So as your lambda is less than lambda p, that's okay. Your section is compact. If that lambda is greater than lambda p, so this means that your flange will be non-compact. Clear? For wave, lambda hw by tw, cylinder concentration 44.6. Lambda p for wave, that is 640 divided by 50 under root. Clear? So this is how 90.50, clear? So let me check one thing. Here we select no, this one not. Here we have basically yes ZX, clear? So we have to look these values, okay, remember, because 50, okay, 50, we have 50, okay. Where is my section? Is my section this one? No. My section, where is my section? 1835, 18 section. It is W1835, okay. Up, going up. Here, this one, W1846, and I think so W1850. So we have to select these values, okay, not those values, remember. So let me choose my pen, and okay, now we check the compactness of our web, clear? And this is also a good news. Your lambda is less than lambda p for web, so the web is also compact, clear? Now, strength checking, including the beam weight, total dead load 5 plus 5. There are external dead load, and now we have to add up the UDL. You can say this is the weight of the beam, 46 kip per feet. Okay, because we are using this section, so 46 pound per feet, sorry, pound per feet. So divided this by 1000, you got this one, and you have to multiply it with 30, so that it will give you total dead load. Okay, if you multiplied it, yes, but you, let's see, here we have, look it to the calculation, pu, and we have wu is how much? 0.046 kip per feet, remember. So your pu will be 1.2 times of 5 and 1.6 times of 15. So I think pu is how much? Let me check it. 5 plus 5, yeah, 5 plus 5. So because we have 2, but yes, okay, this is okay, yes, this is okay. This pu is separately, basically you can say this pu will be equals to 30 kip, this pu, and this pu is separately equals to 30 kip, remember. And one thing, wu, so this is your wu, and that is dead load, so multiply it 1.2, you got this one, clear? Now the reactions are different, clear, and they just draw a new moment diagram, okay, because a little bit greater, okay. 306, you can say 6 kip feet movement is larger, because in the first case without beam weight we have 36, I think so, 10, yes, 300, we have 300 kip feet movement, okay. So it is not larger movement, okay, convert it into kip inch, then you find again your zx, okay. Now find your moment capacity, and that is 340, and your congratulations, your moment capacity is more than the acting load. So that's why our section W1846 is capable for this amount of movement. But now we have to check the deflection limit, and that is a tricky part, which basically you can say affect your design. So let us see. You find out your acceptable deflection, that is 120, 240, sorry, 1.5 inch, and now delta max due to loading is PUA 3L square, already I discussed it. From there W18IX is basically, from this equation they got the IX, that is 712 inch K4. Remember, here they basically ignore the self weight of the beam, remember, okay. So if you add the self weight of the beam, then the formula will be different, remember, okay. And pu is basically, you got the pu value, and that is 30 kip, clear. So you just plug the value, you will got your answer, clear. Now the section has a this section has a moment of inertia is 712, okay, 712, remember. Now we basically determine delta max from this, okay, because we have a section and we just go to the table, and from the table basically we choose the moment of inertia of the section easily, okay. That is not difficult for us, that is 712, clear. So 712 is from table, and now we have to determine delta max, that is the deflection due to the loading. So let's see. Remember, delta max is uh, due to the point load plus due to the UDL or self-weight, and that's things which I explained already. Clear? Because we have UDL and we have point loads. So due to point loads, we have a formula which I already show you on the previous page, and due to UDL we have this formula, and we use this formula in lecture 11, 12, 13, 14. Okay, so we plugged the values and we got a delta max value that is 2.45 inch, and a good news is that your deflection is more than your acceptable limit, so that's why you have to revise your design. Okay, so in lecture number 11, 12, 13, 14, I suggest that you have to choose your section not on the basis of your ZX table. Always select the section on the basis of IX table. If you have to check your deflection limit, remember, already I explained this point in those lectures. Because if you select the section under ZX, although it will pass your first check, that is for movement, but at some time fail in deflection. And sometime basically in lecture number 14 we select the section on the basis of ZX, but they are closely pass basically the deflection criteria. But in lecture 11, 12, 13 they fail. So here we have to revise, and we have to choose now a greater section which can support this amount of deflection. For that purpose, we basically from this formula we use this acceptable deflection, okay, that is 1.5 inch, and we basically put that the acceptable deflection value here, and we got this value now I required. Okay, so let us see. We have acceptable deflection is this much. What we have to determine from this formula IX. So the calculation is simple. You just need to bring this, you need to take IX common. Okay, IX common, IX will be there, remember, IX will be there, and equals to delta acceptable. Clear? Now what you need, IX, just shift IX here and delta X here. This is a simple way. Divide all things, multiply first of all things, divide by 24 divided by EI. You got one value. Clear? Then plus it with the other value which you got. Clear? Then the value you add up and divide it by delta acceptable. You got your IX value, and that value from the first term is this one, and from the second term will be this one. Clear? So do the calculation by yourself. Okay, now IX is basically this much. Now I need to go to the table, that is IX table, and I have to search such a section having a moment of inertia is this much. On the basis of this moment of inertia, if I choose my section, it will pass the deflection criteria, and obviously almost all the time it will pass the first criteria, that is your movement capacity. Okay, so here they say now search the IX table and choosing the section. You have two options, W1871, that is IX 1170, and W2157, that is 1170. So you have two options, either go for what you want. Let's see, let me show you the ZX table. This is the ZX table, and the section which they select, one is I think so W21 2157, the 2157, let me 2157, okay, this one. So this basically this is ZX table, sorry, this is ZX table. We have to go to the IX table. Okay, we need basically this section, remember, we have to come here. Okay, we also use this table as well, but let me show you IX table. So AISC table is basically below of this ZX table, is available below the ZX table. So let me show you where this is AISC table, okay, and here your AISC values and here is your shapes. So you see the values are your values, okay, and here we have this one section, okay, W21 basically having this one section which they select is this one, okay, and the other section which they select W1871, where is this one? This one. Both have same, remember, both have same moment of inertia, okay, but remember W18 having a lower depth, sorry, same, but weight is more. W21 depth is greater but weight is smaller, okay. So let us see. So they choose two section and they do calculation for one section. Let's see for which section. As we are bound to W18, so no, 5 6, yeah, here they say as we are bound to W18, so using W18, I think so in part 1 we are not bound, but let's say they say so accepted, but I think so we are not bound. In part number, yeah, we are bound, sorry for that mistake, we are bound, okay. So we can't use other section rather than W14, clear. So W1871 have a ZX 146. So for this you need to go to your table, where the table is here. You have to scroll up and just going back to that position where we are already there, okay. Here you see W21 is rejected because we can't use this, and we have to use W1871, clear, a little bit higher, W1871, this section, okay. Now you see this section, clear, having a ZX 146, and you need these values, and let me show you this value. We need this value, okay, 544, we need this one, clear. So let's see, ZX is this much. As the load of section increase from 446 pound per feet to 71 pound feet, so again determine the moment we got, okay. So now you have to revise your calculations, and that's you can say the tricky and complicated part of when you revise, because you have to revise all things again, clear, because your weight is changed right now. When you revise your load, you add 71 instead of 46 as we did already, so you got a moment of 308 feet, clear. If you determine the moment capacity of this section having a ZX of 146, it will be 548, okay. You can calculate it, or either you can obtain this from table as well. Let me show you. Here you see 544, directly you can read the moment capacity of this section right here, because they are available here, clear. Now you see, and it is greater than 308K, so just wind up your calculation. Now this is the section which pass both criteria, serviceability criteria or deflection criteria and moment capacity criteria, clear. Now the next part is that we have to choose a lightest W18 section, okay. So W18 section, basically remember, at the first attempt it is difficult to select such a section. You have to 2 to 3 trials, clear. Now the lightest section, W18 section, we need it. As from above calculation, MU is 300 feet without self weight. We did this calculation, okay. our moment is this much without self-weight. If we add 46 pound per feet load for the section self-weight, we see that our moment comes out to be 305 kip feet. You already see this calculation. I did this. Now to find the lightest W18 section, for this we need what? W1840 having a ZX 78.4, okay, and its moment capacity 294, which is less than Mx, so this section will be rejected. W1846 having a ZX 90.7 having a moment capacity more than your Mx, that is 305. So because we did already calculation for W1846 and we know the moment capacity, as we calculated here, we calculated here, right, this one 340. We know the moment capacity, that is W1846 section having a moment capacity that is 340. Okay, so that's why our moment capacity is this one. Okay, so this is our required section W18. And remember, W1871 is the lightest section, which will limit the deflection to this one. These are the conclusions. And W1846 is the lightest section with adequate flexure capacity for the given loading. Clear? And this winds up. These are the results we obtained. You see the calculation work. Please watch lecture number 1 to 6 and lecture number 11 to 14. They are all related to this question. I explain all these things very in depth, so they will help you, okay, to understand this question completely if you have some confusion regarding this. Okay, remember, in this question basically they say using strength level find the lightest W18 section, lightest. So whenever you have to ask that select a lightest section, so you see these bold lines, basically these represents that these are the lightest sections. Clear? So in W18, basically if you search W18 for bold, so you find that W1855 will be the lightest one, and having a moment capacity will be 420. And but although we select W46 basically, okay, so in that case that is our lightest section, remember. And W1850, so although this is not a lightest because this is 50, so W1840, no, this is lightest section, but it having a moment capacity 294, we need 305. So that why we are here we are compelled to use a section in between these two ranges. So we select W1846. Now W1846, basically this section is our lightest section because it has a moment section, moment capacity 340, which is more than 305. Let's conclude. Okay, now let me check it. Yeah, I do these calculations. Okay, see it. Okay, again, that these are my trials. Okay, different trials which I basically make for it to make calculation more simple, and how can I basically select easily a section. Clear? So these calculations only for you. See it once, okay, it will help you. Clear? This is basically for the same question, remember, and I select the same section here. Okay, so these are my just general calculations, okay, which I do for selection of this, okay, of this question. So this is the end of. Watch the videos and enjoy. Thank you for watching.